Alright, so let's go back to one of the previous results that I had done in the class. I would like you to remind it to understand it further. What we had done was that we had a collection of vectors u1, u2, uk, and from there, from these vectors u1, u2, uk, we looked at a linear span ls of s, and then from that linear span we picked up certain vectors t. Fine. The only important thing that we said was that the number of elements in T is more than the number of elements in S. So, what we said was that number of elements in T, fine, and that implied that T is linearly dependent. Fine, that was the idea. And what do we do it? We wrote the combinations as this, different combinations. And from there we wrote the W's in whatever way we could. At the next stage, what was there is that we had this matrix for us, some sort of matrix representation. We had W1 to Wm, writing it as, so I have a matrix of W which is consisting of W1 to Wm, and I am writing W as U times a matrix A, and U was again a vector of u1 to uk, fine, and A was your whatever the size of the matrix that I have, I do not worry about it, but there is some size that is coming into play. So, we wrote a collection of vectors as vectors into a matrix, fine. In here I looked at vectors as column vectors. I could have also done here, written it as W1, W2, Wm here, and then written here u1, u2, uk, and now you can see that the first one was a11, u11, a12, u2, a1k, uk. All right, that was the first vector, that was W1. If I want to get W1, now I will have to write the matrix as W1 is a11, u1, a12, u2, and a1k, uk. Fine. So, I will now get a matrix which is of the type M, so it is M cross K. Fine. So, now let me put it everything in the next page and have a better clarity of things. All right. So, what I am trying to say here is that I have a collection of vectors. So, I have collections of vectors say U, which is I am writing it in terms of columns or rows, whatever it is, uk. I could also write in writing it like this, I can also write it as say S, say U tilde as U1, U2, UK. So, depending on what way we want to write, we can write things here, fine. Similarly, I had W, so I had, I think I wrote it as W1, W2, WK. Similarly, I can have W tilde, which is W1, W2, WK. All right. So, depending on how our vectors are, how we want to represent, we can say that U or W looks like U times a matrix. So, this is in terms of the rows here. If you look at here, this is the rows. So, it is a row vector, or each vector is a column, each vector is a column, fine. Here these vectors are column vector, but we are writing it each of these UIs or WIs are row vectors. So, depending on where I am, I can look at things, fine. So, this is one way of writing it. If I want to write using this idea, then W tilde will be equal to A times or depending on whatever A is, this A and this A could be different. So it was basically transpose, if you see nicely, B times U tilde, all right. So there are different ways of looking at things. Here I wanted to look at W times X transpose was U times A X transpose, or if I want to write X as a vector, then I have this nice way. Otherwise, if I want to do it here, this is a column vector, so I'll have to write here Y transpose W tilde as Y transpose B U tilde. Then it will make sense. Then I can say that I am looking at linear combination of vectors of W tilde. Fine. Here I am looking at also linear combination of vectors of W. So the vectors are same. Here in W tilde the vectors are W1 to Wk. In W also they are W1 to Wk. Fine. But it is the way of writing which makes all the difference. If you want to write like this, then you have to look at the system Ax is equal to 0 for linear independence dependence. So this is for linear independence, all right. If I want to look at from this point of view, so I want to look at this, so that will give me that I am to look at Y transpose B is 0, and then again I am looking at, again this is for linear independence. So depending on what representation I have, I need to look at Ax equal to 0, or I have to look at Y transpose B equal to 0, which is equivalent to saying that B transpose Y is 0, all right, fine. So where you have to multiply, what you have to do, and how do you use your theorems of infinite solutions depends on you. You have to be clear about it, fine. So be careful when you make statements. You cannot just do whatever way you like, fine. So here if I want to look at, again here it is, if I want to look at infinite number of solutions for this case, I need to look at columns of B transpose and rank, fine, which is same as looking at, which is equivalent to looking at rows of B and rank, but rank remains the same for us. Therefore it is, here it is rows which play the role, here it was columns which played the role, fine. So you have to be careful when you say what are free variables, what are basic variables and so on. It will depend everything on these ideas where you are looking at, fine. So sometimes you have to look at Ax equal to 0, sometimes you have to look at B transpose Y equal to 0 to make sense of things, all right. So now with this idea, let us start further. Also recall that we had done what was called a basis of a vector. So all right, we have the notion of basis of a vector space V over F, all right. Most in our example, as I told you from the very beginning, it will be real numbers, once in a while it will be complex numbers, but most of the theory is true even for fields which have finite number of elements like Z5, all right. So you just have to take things and have clarity of things, fine. So what is the basis? The basis was, all right, either it was a minimal spanning set, all right. Also I am assuming here that my vector space has dimension finite, dimension of vector space V is finite. So suppose that it is n, fine, it is finite. So it has minimal spanning set, this is what a basis is, or I can say it is the maximal linearly independent set, or the third was a set which was linearly independent and spans. So if I want to show that something is a basis, any three can do, and we have seen the basis for us. So let me remind you once more. So, basis examples. First example, if I look at Rn, the basis consists of E1, the standard basis, E1 to En. This is the standard basis. So, what I am saying is that if I look at R3, this corresponds to 1 0 0, 0 1 0 and 0 0 1. If I am looking at say all 2 cross 2 matrices, fine, then I have basis as 1 0 0 0, or let me write it 2 cross 3, 0 0, 0 1 0 0 0 0, 0 0 1 0 0 0, fine. So, I would like you to find out how do you get these matrices, that is more important, all right, using these ideas, fine. So, try that out. For example, if I want to write this is 1 0, since it is 2 cross 2, so on the left it is 2 and on the right it is this. So, if I multiply these two matrices, I will get this part, fine. What about this? This is nothing but again 1 0, but we multiply it to 0 1 0, fine. For example, if I want to look at this matrix, look at 0 and 1 and multiply it with 1 0 0, all right. So, they are basically coming from these ideas itself. The sizes are different, so you have to be careful about it. So, this matrix, for example, we write it as E1 1, this as E1 2, fine. This is E2 1, that is second row and first entry. This is E2 3 and E2 2. Fine. So, different ways of writing it, but you need to understand all of them, fine. Another example is set of all polynomials with real coefficients. So, its basis is going to look like all polynomials of different degrees. So, there is no end to it, it just goes on and on, fine. Now, all right, one more example, I think I should look at one more example. So, consider this, no, all right. So, now let me look at what are called fundamental spaces. Spaces associated with a matrix, all right. So, this will give me a lot of examples, and for them we can look at the basis, fine. These are fundamental spaces. So, I have a matrix A which is M cross N. I define certain things, what is called column space of A. So, let me write I think full form here and then the column space. So, it is column space of A. The notation for this is COL of A, and this is defined to be equal to column. I am looking at all the columns. So, I am looking at A times X, X belonging to Rn. Is that okay? Fine. This is the first space. Second space is, we have already seen this also, null space of A. We write it like this. Many books they will write it as this. So, whatever way you want to write, you write it. This is all X belonging to Rn such that Ax is a 0 vector. So, I am solving the homogeneous system. Third is called the row space of A. Even though it is called row space, I do not write row here, because in most of the books they look at that way. So, we look at it as column or space of A transpose, because the rows of A are nothing but columns of A transpose. So, therefore, we write it as column space of A transpose. So, therefore, this is equal to A transpose Y, Y belonging to Rm, fine. And the fourth is what is called a left null space of A. So, it is nothing but null space of A transpose, which is nothing but all Y belonging to Rm such that A transpose Y is 0, all right. So, please try to understand what they are. So these are the different definitions. What is called column space? So if I look at column space, I am varying here, x is varying over Rn, but what is the size of these vectors? If I look at the size of this vector, A is m cross n, x is n cross 1. So I get here this is size is m cross 1. So this is a subset of Rm. Fine. This is looking at all x belonging to Rn. So this is a subset of Rn. What about here? A transpose, if I look at, this is of size m cross 1, y is m cross 1. So this is n cross 1. So this is a subset of Rn. And this again you can see here that this is a subset of Rm. So what I am looking at is, I have got two subspaces which are coming from Rm and two subspaces coming from Rn. Is that okay? So we need to understand them, what is the relationship between them, and how do I come across all those things. Is that okay? Fine. So let me try to define a function now for you. So I define a function f from Rn to Rm. I am defining a function. So define f by f of x is equal to a times x. Fine. So domain of this function, if I look at the domain of this function, domain of f is Rn. Fine. What is the codomain? Codomain of f is Rm. Fine. So therefore, if you look at these fundamental spaces, all right. So the first two, first and the last one, first and fourth, they are coming from the codomain, and the second and third they are coming from the domain. Fine. So basically they have come from functions. So if you remember, in our school days we used to learn, given a function, what is the domain of the function. Codomain was fine, but more than codomain it was looking at, fine, what was looking at? The range of the function. So there was a notion of what is called the range of a function. Fine. So I would like you to see that this is nothing but the range of f. Why range of f? Look at this. Range of f by definition is f of x, x belonging to domain. Fine. Which is same as ax, x belonging to Rn. Fine. This is what it was. Then we looked at, so that was looking at given a function, we looked at domain, codomain, range. Range is same as the column space of A in this case. And we also did many things like f is 1 1, f is on 2 and things like that. Fine. So how does we get ideas about 1 1 and on 2? So it turns out that I am looking at functions which are of this type, which are called linear functions, which we will come to afterwards, or linear transformations. Because of that, it will tell us that I just need to understand the null space to say whether the function is 1 1 or onto or not. Fine. So the idea is we need to understand these spaces so that you can go back and understand whether f is 1 1, whether f is onto, what is the range of f, whether where is the function defined, and so on. Is that okay? So let's go and build up these ideas for us. You can check that column space, I am saying it is a space, it is a vector subspace of Rm. Null space is again a vector subspace, but it is a subspace of Rn. Column space of A transpose is a subspace of Rn. Fine. And you can see that they are somehow related, that you can see, and we will prove them first. So before doing that, let us look at some examples to have a better clarity. All right, example. All right. So I have A is given to be equal to 1 1 1, 1 2 minus 2, 1 minus 1 7, and minus 2 1 minus 11. Fine. So what we do is that we want to look at what is the row space, column space, and so on. So let us apply the RREF, try to get the RREF of this. Fine. I am doing it slowly. So 1 minus 1 is 0, 2 minus 1 is 1, minus 1 is minus 2, 1 plus 2 is 3, 1 minus 1 is 0, minus 2 minus 1 is minus 3, 7 minus 1 is 6, and minus 11, so 1 minus 1, yeah, so minus 11 plus 2 is minus 9. All right, this is what I have. Just like it, just verify it. 1, 1, 1. So I'll verify it once I get the final thing. So let me see 1, 1, 1 minus 2, 0, 1 minus 2, 3. Fine. Now this matrix, the last row is 3 times minus 3 times this one. So minus 3, 6, minus 3. So I get 0, 0, 0, 0. Fine. I can rewrite this as again further. I have got 0, 0, 0, 0, 0, 1, 2, minus 3. I can use this to make 0. So 1, 0, this minus this. So 1 plus 2 is 3, I hope. Minus 2 minus 3 is minus 5. All right. So this is my RREF of A. Fine. I have got the RREF. Now from here I want to conclude all my ideas. All right. So now what it says is, let's look at this matrix carefully. The pivots were, these were the pivots. Fine. Since these were the pivots, the first and second, so it implies that first and second column of RREF of A are linearly independent. Fine. So if I look at A is nothing but some P which is invertible matrix, times the RREF of A. Fine. Now we are saying that the first 2 columns are linearly independent. Fine. So let us go back. So go back to this idea of writing vectors in terms of whatever way you want. Once you have written it, then you can see that this will imply that the first column of A and the second column of A are linearly independent. Fine. So just have a look at it. You can see that they are linearly independent. So what I am writing is this is a linearly independent set. All right, the first 2 columns. You can also see that I can get the third column, all right, in terms of the first 2 columns. How do I get it? Think about it for yourself. Is that okay? So how do I get the third one? You can think of this as system of equation and you are trying to solve it here. So it is 3 times the first one and 2 times the second one, something like that, minus 3, minus 2 and so on. Think about it, how do you get it? Fine. You can also say that here you can see that first and third are also independent because I cannot get this column from here. Fine. So you can see that first and third are also independent. Fine. Similarly, first and fourth is linearly independent, second and third is linearly independent and so on. At the same time, you can see that if I want to look at this first column, second column and the third column, then this is a linearly dependent set. Because you can see that in the RREF, look at the RREF, in RREF of A, if I look at this matrix, suppose I write this as R, then what I can see here is that the third column of this is equal to 3 times the first column plus 2 times the second column. All right. I hope I have done the calculations correctly. So No, there is a mistake somewhere, I think, because minus here. So there is a minus here, I should have done minus here, that was a mistake. So there should be a minus here, 2 times this, fine. So now you could so just verify this, if this is true, I can multiply p on the left throughout. So I can multiply by p here, p here, p here. Once I have done that, I get that a of this is equal to 3 times a of this minus 2 times a of this, fine. Just verify it. So 3 times the first one, it is 333, fine, minus, why I am not getting it? No, I think I am getting it. So 2 times this one, so 2 times 1, 2 minus 2, which is same as 333 minus 2, 4 minus 4, yeah, which is 1 minus 1 and 7. 1 minus 1, 7, which is your R third one, fine. So you can see that I have computed the RREF. Generally, RREF is done to solve a system of linear equations, but in place of solving a linear system, it has also given you something more, that is, I am able to say what is happening to the columns here. You can similarly check here that in this example, that the 4th row of A, all right, 4th row of A, or 4th column of A, sorry, is equal to minus 5 times, just look at here, minus 5 times the first one and plus minus 3 times the second one. See, again there is a mistake here, so this should have been 3 here. So plus 3 times a of this, all right. So I wrote it wrongly from there, so therefore you are not getting it. So you can see that everything is nice here, you can get things. So the idea is, whatever is true for RREF, you have that for you, apply P to it, the matrix which gave you RREF, and then go back to A. Is that okay? That is one thing that we got. So we have said that these are linearly independent, the first 2 columns. Further, let us look at these 2 rows. These 2 rows in themselves are linearly independent, fine. Since these are linearly independent, so you can get again that, I think I should write it down the next line, otherwise I will have a problem. So for me the matrix is there, but RREF, I want the RREF of A. So RREF of A is 1, 0, 3 minus 5, 0, 1 minus 2, 3, 0, 0, 0, 0, whatever A is, that let us not worry about it, fine. So this is my RREF of A, these were the pivots. So we are saying that row space of A, which was same as column space of A transpose, its basis is going to be 1, 0, 3 minus 5, this vector, and another vector is 0, 1 minus 2, 3. These are the 2, all right. In this example, it turns out that I have not done any row interchange, not done any row interchange, and therefore the first 2 rows, the first 2 rows of A are also linearly independent, fine. So if I had done interchange, accordingly I will have to go back and then see which were the rows which gave me these as the pivots and things like that, all right. So whatever rows I have, accordingly I will have to go back to A and then get my answers. That is the basic idea. So what we have done here is that I have been able to get what is the row space of A. So row space of A is nothing but column space of A transpose, which is generated by these 2. Think about it, fine, how I can write it out. So please check that this turns out to be x, y, z, w this belonging to R4, such that 3x minus 2y minus z is 0, 5x minus 3y plus u is 0. Column space of A we already computed also, there also What was that? Column space of A was x, y, z belonging to R4 such that 4x minus 3y minus z is 0. I would like you to see that. Null space of A was x, y, z, w belonging to R4 so that x plus 3y, sorry, x plus 3z minus 5u is equal to 0, y minus 2z plus 3u is equal to 0, and null space of A transpose is x, y, z belonging to R4 so that x plus 4z is 0 and y minus 3z is 0. This is what I am writing here, but let us try to understand from where did I get it, how did I get it, fine. So, here I am saying that these are in the, so if I want to look at the row space of A, all right. So, row space of A is generated by these two vectors, fine. So, it is alpha times this plus beta times this. So, it is supposed to be equal to linear span of the vectors 1, 0, 3, minus 5 and 0, 1, minus 2, 3, fine. So, you are supposed to check whether they are okay or not. So, if you remember what we had done was to check things, we need to look at the system which was 1, 0, 3, 5, 0, 1, minus 2, 3, look at x, y, z, w and get the conditions. So, you can see here that there are 4 equations here, only, all right, there are 4 equations for us, and therefore, we will need here 2 conditions to come into play. You can look at that. So, just look at this part, it says here that x, y will remain as it is, I can cancel out z, I can cancel out w. How do I cancel out z? Look at z, if I want to cancel this out, this vector, so this vector is nothing but 3 times x, just remove the first one, 3, this row minus this row will give me this part 0 and this plus this will give me 0, all right. So, I just need to add this, so minus 3x plus 2y, so just look at this part, this, all right, should be equal to z, so that they cancel out. So, what I am saying is I have got 1, 0 x, 0, 1 y. So, I just multiply by 3 and subtract, I will get 0 minus 2 z minus 3x. Again I want to make this 0 again, so I will have to do with the second one. So, I will go from 0, 0 z minus 3x plus 2y, all right. So, for this system to have a solution, I will need that this is the condition and which is this condition. Similarly, the next one will give you this condition. Is that okay? Fine. Column space of, again you can get it, that is okay, or you can just look at whatever you have, try to get them yourself. What I would like you to stress on is trying to look at examples and verifying things on your own, fine. So, just go back and see whether they make sense to you or not. So, for example, if I look at my matrix was 1, 1, 1, 1, 2, minus 2, 1, minus 1, 7, minus 2, 1, minus 11. So, you can see that I am looking at column space of A, look at these two vectors 1, 1, 1, 1, 1, 1 will give you 0, 1, 2, minus 2, if you just plug it here, you will get that 4, minus 6, plus 2 will give you 0, all right. So, these two were the basis elements, as I said, they satisfy this, fine. You can also see that something more is important, that will come to in the next class. Thank you for now.